Let's take a look at example 2 from section 7.3. In this one, we want to find the inverse Laplace transform of 2s plus 5 divided by s minus 3 squared. A common theme that we saw in the previous examples is that we want to kind of decompose the inside function using partial fractions. So we have 2s plus 5 divided by s minus 3 squared. And this is the case where we have a repeated linear factor in the denominator. The way this will break apart is because it's a linear factor, we would need a polynomial of degree 1 less in the numerator, which of course would be a constant term, and then every power up to the maximum of the repeated factor has to be present. So we would also need the s minus 3 squared, and again that would need to have a constant in the numerator. Let's go ahead and see if we can solve for this. We can go ahead and multiply every term in the equation by the common denominator. That's going to be s minus 3 squared. When we do that, we're going to get 2s plus 5 is going to be equal to a times s minus 3 plus b. As I've mentioned before, there's more than one way to solve this from this point on, but typically if you have irreducible quadratic factors or even repeated linear factors, a lot of times it's helpful to equate coefficients. Here we can do a kind of a mixture of the bunch. If we let's say s be equal to 3. When s is equal to 3, we would get 2 times 3 plus 5 is equal to, this term here would be 0. So this would be equal to b, which tells us that b is going to be equal to 11. And now that we know that b is 11, we can plug that in directly. So 2s plus 5 is equal to a times s minus 3 plus 11. And now choose any other value for s besides 3 in order to solve for a. I think perhaps a convenient choice would be s equals to 4. If I plug 4 in, I would do 2 times 4 plus 5 would be equal to 4 minus 3 is 1, so this is going to be a 1a plus 11. This is going to give us a 13 equals a plus 11. Subtract 11 from both sides, and we would get that a is going to be equal to 2. So we're able to do our partial fraction decomposition. This is going to be the inverse Laplace operator of a over s minus 3, which is 2 over s minus 3 plus 11 over s minus 3 squared. Of course, we know that the Laplace operator is linear, so we can rewrite it like this. It's going to be the inverse Laplace of 1 divided by s minus 3 plus 11 times the inverse Laplace of 1 divided by 3, it's going to be s minus 3 squared. Using our properties of the inverse Laplace, we know that this one here is simply going to be e to the 3t. And then we have plus 11. And now let's focus on this term right here. One of the things that we know is that the inverse Laplace operator of 1 over s squared, we know that that thing is going to be equal to t. And we're going to invoke that shift theorem that we just saw a little bit ago. So let me kind of remind you of that. This was the inverse of what we called Theorem 7.31, and it said the following, that the inverse Laplace of f of s minus a is equal to the inverse Laplace of f of s, with the translation s goes to s minus a, and this is equal to e to the at times f of t. So essentially what's going to happen here is we know the inverse Laplace of 1 over s, that's going to be t, but because of this translation, we're going to get not just a t term, but we're also going to get an e to the 3t. So all together, that inverse Laplace is going to give us an e to the 3t times our t because of the translation. Okay. So example 2a is kind of a really good one. It kind of reminds us of a couple of things. It's a little bit of extra practice and review of your partial fraction decomposition information. In particular, it's a good review of what happens when we have repeated linear factors. And this is the first time we've had a chance to kind of use our translation property when we have a inverse Laplace of a kind of a shift function, or translation they would call it. Let's go ahead and do another one. In example 2, part B, let's do the inverse Laplace transform. Sorry, my L's are getting a little sloppy. That's better. Let's do the inverse Laplace transform of s over 2 plus 5/3 all divided by s squared plus 4s plus 6. So normally speaking, we would start out the same way, in that we would try to factor the denominator, because we would like to do a partial fraction decomposition. But one of the things that you would find is that this denominator, this s squared plus 4s plus 6, not only will it not factor, but if you try to use the quadratic formula to write it as, let's say, x minus a real root times 1 times x minus a second real root part 2, that's not going to work, because this quadratic would actually have complex roots. So what do we do in the situation where we have an irreducible quadratic within our denominator? Well, what we're going to do is we're going to complete the square on this. Okay, so we want to rewrite this denominator by completing the square. So we have our s squared plus 4s, and then I'm going to move that constant term of 6 over here. If you recall, what it takes to complete the square is if you have something of the form ax squared plus bx. To complete the square on this, you need to add half of the coefficient of x squared. So we need to add half of 4 squared, but then if we're going to add it, we would also have to subtract it over here, so that we're not changing the value or the form of this thing. This gives us s squared plus 4s plus 4 divided by 2 is 2, and then 2 squared would be 4. And then we have plus over here. Obviously this was going to be 6 minus 4, which would give us 2. And the reason why we do that is when we group these two things together, this now creates a perfect square. It's going to be s plus 2 squared plus 2. Okay. So we now have our denominator as a perfect square. So we can rewrite this as the inverse Laplace of, we have s over 2 plus 5/3 divided by s plus 2 squared plus 2. And already we can tell that there's somewhat of looks like a shift that's kind of coming in. And so now what we would like to do is we want to kind of move the numerator around a little bit, so that we would also have kind of like an s plus 2 in the numerator. Okay. So we completed the square in the denominator already. And now we're going to go ahead and kind of rewrite the numerator. So in our numerator we have this. We have s plus 2. That's an ugly looking s. That's prettier. So we have s plus 2 plus 5/3. Let's take the 1/2 out from the s. Okay, because we don't want to have a fraction times s. We want to think of it as the variable s, which incidentally should match up with the expression we have in the denominator, and then we have our plus 5/3. If I have an s plus 2 on the bottom, then I would like to have like a variable term of an s plus 2 up top. Okay. Now that plus 2 that we just added, we have to account for the fact that we just can't simply add coefficients to this. If I add a 2, then over here I'm going to have to subtract a 2 as well. But I didn't really add a 2. We actually added half of 2, which is 1. So essentially I've added 1 to this expression, which would mean I would need to subtract 1 over here. So this is 1/2. We can write it as s plus 2, and then 5/3 minus 1, getting common denominators, would give us 2/3. So we're going to rewrite the numerator like this. This is still equal to, this is the inverse Laplace transform of, we have 1/2 s plus 2 plus 2/3. We have s plus 2 squared plus 2. And now what we're going to do next is we're going to use linearity of the inverse Laplace transform to rewrite this thing. We can write it as 1/2 times the inverse Laplace of s plus 2 over s plus 2 squared plus 2. And then we have a plus 2/3, the inverse Laplace transform of 1 over s plus 2 squared plus 2. And now that we're here, we should be able to finish it off. If we look at this first one, okay, essentially what's going on here is we have the translation. So we have like an s plus 2 and an s plus 2. So the form of this first one, it really looks like this. It's 1/2 the inverse Laplace of, we essentially would have like our variable s, we have an s squared plus 2, but we also have the substitution, where it's not just a basic s, our s was replaced with s plus 2. And the reason why we want to write it like this is because for us, this should be a known transformation. This is 1/2. This thing here, remember, we need a square here. This would be like the square root of 2 squared. So the a has the value radical 2. So that would give us a cosine of the square root of 2 times t. But because of the shift, we get an e to the negative 2t as a result. Okay. So that's the inverse Laplace transform of the first thing. And then similarly, if we come over to this next one, we have a plus 2/3, the inverse Laplace of 1 divided by s plus 2 squared plus 2. And what I want to do is kind of rewrite it in the same way. Let's think of this as a shift. So maybe I'll call it this. I'll call it 1 over s squared plus 2, where s is being replaced with s plus 2. Again, we can think of this, if it helps, and it might, as this 2. You can think of it as the square root of 2 squared. Now, whatever constant we have here, we would also need to have that same constant within the numerator. So we're going to multiply this by a form of 1. Let's put a square root of 2 up top by putting a square root of 2 in the denominator on the outside. And now that we've done that, we should recognize the form. So we have this constant, 2 divided by 3 square roots of 2. The form of this thing right here, that would be the sine of the square root of 2t. But because we have the shift, we're also going to get an e to the negative 2t with it as well. So there is our inverse Laplace transform for this one. It's 1/2 e to the negative 2t cosine of the square root of 2t plus 2 divided by 3 square root of 2t, square root of 2 e to the negative 2t sine of the square root of 2t. The biggest takeaway from this one is a couple things. So our denominator this time, it was an irreducible quadratic factor. And because it was an irreducible quadratic factor, one of the things that we wanted to do, first of all, is we wanted to write the denominator as a completed square. So complete the square in the denominator for the variable s, and then whatever you have. So if you complete the square, eventually it's going to look something kind of like this. You're going to have, generically speaking, s plus some constant squared plus some other constant here. And generally speaking, we like to think of that constant as being squared, whatever. But then what you also want to do is you want to have essentially the same kind of term in the numerator. So you want to kind of, factor out whatever you need to do to also make that same kind of variable appear in the numerator so we can treat it as a shift. So here's an example of this. This was example 2b.